Hi everyone. I'm Arshad. I'm going to talk about multiphysics eddy-current simulations for hybrid electric aircraft propulsion. So why are we doing this? Well, the aviation industry is growing an increased amount of pressure to move towards alternative methods of air travel. So for example, currently we use jet fuel, but we're trying to cut down our CO2 emissions. One option is electric motors. But these have a lot of problems, one of which is the high power density requirements, which in turn will increase the temperature and thus the material properties of the actual motor itself. And therefore, we need to be able to simulate all of this for design. And this is working with Rolls-Royce, who are basically sponsoring me for this project. So what type of problem are we actually looking at? Well, we're looking at eddy current problems. And the idea is that a time-varying magnetic field induces a current on a conductor, and this in turn can cause energy losses due to the heat dissipation, and modeling this is obviously of key interest, and therefore also modeling the nonlinearity effects associated with it. So how do we model this? Well, let's go back to Maxwell's equations. So Maxwell has four fundamental equations. So we have Gauss's law, which talk about the electric flux and its relation with charges. We then have Gauss's law for magnetism, which say that there's no magnetic monopoles. We then have Faraday's law, which basically tells us that a time-varying magnetic field induces effectively an electric field or a voltage. And then finally, we have Ampere-Maxwell's law, which talk about the current and how that creates a sort of a rotating B field or a magnetic field. But for eddy current problems, we can neglect the capacitance effects. And so our equations get simply are these four here. Now, often in electromagnetics, we use potential formulations. And the reason we do that is we have four equations, and we need to try and reduce that to a much more sensible amount. So we use the potentials. So if we say A is our magnetic vector potential, we can define B as a curl of A. And the advantage of this is that it guarantees a divergence-free constraint automatically. We then have the electric field, and this is defined as the grad of a scalar potential V, and against its time derivative, it's actually a time derivative, not dA dV, of the magnetic vector potential. And the advantage of this is that it provides a voltage-driven condition. Now, for the function spaces for these problems, we use the H-curl or Nedelec elements for A, and this has obviously been supported with literature, and H1 Lagrange elements for the electric scalar potential. So how are we going to solve this type of problem? So here we have our motor, and we're going to use the mixed domain formulations that we can use in FEniCS. So we have a non-conductive domain, and we have a conductive domain where the eddy currents are flowing. And so we're solving these two equations. So in our conductive domain, we're simply solving the curl-curl problem. And in the non-conductive domain, we're solving the curl-curl problem on the parent mesh. And on the conductive domain, or our submesh, we're solving this AV formulation here. And for the coupling and the nonlinearity, we're using, calculate our J field through sigma E. And our Joule heating is calculated from Q. And our nonlinearity is using the non-Newton's method, where our preconditioner is reused every iteration. And the Jacobian is calculated using the UFL derivative. But there's a big challenge with Maxwell's equations, and that's because of the large null space associated with it. So if we go back to our curl-curl term, we have this large null space of gradient fields. And this causes a big problem, because classic AMG methods often fail. And at best, the iteration count just blows up. And this is because it can't isolate the high frequency and the low frequency modes. So we need to find an alternative preconditioner for this problem. And one such preconditioner is the AMS preconditioner developed by Hitmer and Zhu. And the idea is that you get your solution, and you can split it into three different separate solutions. So you have this VH term, which is our high frequency modes. We have our nodal auxiliary space, which is effectively a vector Poisson, and then we have our gradient fields, which are solved through a scalar Poisson problem. And so we can apply AMG on the gradients and the nodal auxiliary space, and we can apply a point smoother of our choice for the high frequency modes. Now, for the Poisson block from the scalar potential, we can just use our classic Boomer AMG. And so our block preconditioner looks something like this, with the fact that V is only solved in the subdomain and A is solved in everywhere. Now, the one thing which is tricky as well is with the subdomain, we're assuming that the conductivity of our non-conductive region is 0. And what we need to do is Hyper has a function now which had a bit of a bug, but I managed to fix it. And the idea is called the interior nodes. So we locate exactly which are the nodes interior to the conductive domain, and then we basically create an array, and then that gets passed into our preconditioner, where a new restricted discrete gradient matrix is formed. And then that way we can then solve our problem as shown. Cool. So the results I'm going to show you is from a Team 24 benchmark. So this is a 3D model. They provided us with a nonlinear BH curve. In this case, I've modified the model. So initially it was a looped coil, but I've modified it so that you have this sort of horseshoe coil. This way I can apply sort of a voltage here and a ground voltage here. And so sort of using the advantages of the AV formulation. So here are some of the results. So you can see the B field and the J field, and we can see that the temperature as well begins to rise as a result from this problem. And this is just purely on the conductive domain in our rotor and stator. For a nonlinear problem, we sort of, like I said, we reuse a preconditioner every iteration. This needs to be optimized. This is obviously quite recent work, but the idea is that we implement this BH curve and we get our nice results here. Now, often in industry, one of the key things people do is they use conductivity of a very small amount. Now, this has a couple of disadvantages. One of which is that because you're applying an artificial conductivity, the real conductivity of air is around 10 to the minus 14. Using that often breaks your solver. So that's one of the reasons why I use conductivity of 0. Another reason is that you can't exploit the mixed domain method, as you have effectively a conductivity everywhere. And as you can see here from some of the results, the average iteration count sort of remains quite fixed and is a lot lower when using a conductivity of 0. Finally, as I said earlier, one of the key things we're looking at is exascale computations. So this result here is a weak scaling where I use around 100 DOFs per core. So we're trying to see how the processing power of each process. And we can see that generally this exhibits a nice weak scaling results. And then finally, for strong scaling, we did it on a 10 million DOF mesh, and we get pretty good parallel scalability using Hyper as a preconditioner. Finally, for the future work, well, right now I've just implemented a heat transfer model from dual heating, and separately with the nonlinearity effects. But the idea is we need to sort of combine them together because the nonlinearity from the temperature causes the nonlinearity effects is caused by the temperature, so we need to couple them together. We're also looking at coupling into fluid flow to try and get some cooling on our problem. And for higher ordered elements, it's important to look into GPU architecture, and finally load balancing to further optimize our solver. And yeah, thank you very much for listening.
Thanks a lot. We have time for a few questions. Yeah.
You mentioned in one of your slides, I think it was slide 28.
Mm-hmm.
Yeah, is that really the magnetic field in Tesla that you have in the first?
Yeah, so this is from the Team 24 benchmark model. So that's what they've given.
10,000 Tesla.
Yeah, it's not. This is from the model they gave, right? This is not like a model I've made. Yeah.
Did you model the rotation of the rotor?
No, that's something I need to do as well. Yeah, that's the next step. But you can just apply a motion voltage term.
Because that will change the heating as well.
Yeah, exactly. Yeah. So that's something for the next steps as well.
As So what's the bottom line? I mean, these are motors for electric aircraft. Where do we stand on that?
Well, hopefully we'll get some electric motors going for aircraft, but at the moment it's sort of like proof of concept. I think the key thing is to simulate this, we need to get large exascale simulations. And right now we don't have something. Commercial code is just not good enough. And so this is sort of what we're working with Rolls-Royce. Hopefully we can get electric motors going.
Do you have other questions? If not, I have one. So can you explain better the precondition with the interior points? I mean, it's kind of a geometric precondition in a way. Or?
Yeah, so the idea is that this gradient, this is a discrete gradient field, which sort of maps our nodal points with our edge points. And the idea is that with the interior nodes, we're just telling it which points to basically focus on. So it basically creates a new restricted discrete gradient matrix, and then that's applied for the as a preconditioner. Okay. There was a bug earlier on in Hyper, but it managed to sort of fix that. So that was, yeah.
Thanks a lot.
Thank you.
Thanks.